Have a carbon metal covalent bond is considered to be organometallic. So it contains a carbon metal bond, and I want to emphasize here this is covalent, not ionic. So it's covalent. These things are violently reactive with water, so they are highly reactive with any acidic H. So highly reactive with acidic H's. So we already do have some limitations on what we can use here. So we basically can't use an alcohol for a reaction here because they're going to react with the Grignard or with the whatever organometallic reagent we're using. Generally, the way you want to think about these reagents is that they're kind of like a C- reagent. So think of them as C-. So with that analogy here, we can think of why they would be so reactive. So imagine here we have this bond, and in order to get a C- via this way, you get an H+ and a C-. You guys recall what the pKa of this reaction is. They're about 50. So these are probably the weakest acids that we're going to deal with out here. So these have if it's an alkane CH, the pKa is about 50. So if you remember here that these are this is the logarithmic scale. So essentially what this is saying is that you're going to have 10 to the 50 of these ones to 1 of these. So it definitely very much favors the left side here. So the problem with this is that if you have any acidic H's out here, it's going to prefer the reverse reaction. It's going to prefer to get rid of that carbanion that are highly reactive. It's going to go back to that. So we're going to see in all these that typically the quenching step is to add water. It's typically how you stop the reaction, is you add water to it. All right, so a few other comments here is the reactions are often in ether. So diethyl ether, the common one here. And it has to be anhydrous. What does it mean when we say it's anhydrous? So that means that there's no water. The way that organic chemists typically refer to an anhydrous solvent is referring to it as being dry. So when we use the word dry in organic chemistry, we're not referring to no liquid, we're referring to no water. So we say a dry solvent means no water whatsoever. And I actually worked in a research lab where we had dry solvents all the time, and we basically had a permanent distillation apparatus set up for all the solvents we needed. And I would just go in the hood and go, okay, I need ether today, and just turn it on, and then take my solvent out after I distilled over, and then replenish it before I left for the lab for the day. Otherwise, you got yelled at if you didn't replenish the stock before you left. All right, so I have a couple reactions here. I wanted to go over the organolithium reactions and the Grignard reagents today. And I do want to point out we're not going to finish all the organometallics today. We're going to come back to the stuff a couple times throughout the semester. All right, first things first, organolithium. So I'm not going to go over the mechanism and how these are formed. I am going to go over the reactions on how they actually work with organic compounds. So in general, what we do is we take an alkyl halide. So that is your Rx, that's your alkyl halide. Let's use purple for that. Alkyl halide plus 2 moles of lithium metal. That's the metal there, not the ion. Super reactive with water. And we have to have ether as our solvent, Et2O, and we will get the organolithium compound, which is this. If we're worrying about mass balance, what is left over for mass balance? We have lithium and whatever the halide is. So if it was a bromide, it would be LiBr, chloride, LiCl, whatever. So just LiX for short. This would appear in the flask as probably a white precipitate forming, but it's in the ether solvent, not water. That would dissolve in water. All right, when you see these reagents here, remember, just like our previous example here, you want to think of them as a carbanion and Li+. That's not exactly true, but the way we work with them, that's what we're going to do with them. Okay, so let's go ahead and be specific here, and then I want to go ahead and show you guys a couple of reactions we could do with them. All right, so here I've actually run this reaction personally. So the bromine version here, and then we have 2 moles of lithium and ether, and you get 2 moles of your butyl lithium and LiBr here. Okay. I also do want to point out in this reaction, the hybridization on the carbon that has the bromine does not matter. It can work. Let me show you another little side note here. It does not matter if it's on a benzene ring or a triple bond, whatever, it works. The chemistry here is different than what we're used to. We're not going over it in this class. If you take an inorganic chemistry class, you will cover this mechanism. All right. So my little funny side story here, I'm actually going to pause it for this. I don't want this in the video. All right, so we made the butyl lithium reagent earlier, and then you can react this in any situation for SN2 as long as you don't have any acidic H's around, then it works fine. So let's go ahead and take a look. So we have this here. So you're going to go ahead and do the backside attack, but the way we draw the arrow is different. So I'm going to show the arrow coming from the bond, similar to what we saw with the alkene reactions last semester, and kicks out the leaving group. But notice here, I'm not writing out C-, I'm just treating the bond here as my nucleophile. So once again here, the bond in the reaction is the nucleophile. On these reactions, you need to be careful of your carbon count. So we had 4, and then we have a new bond, which I'm going to highlight in purple right now. So purple, that's our new bond. And then it says 2 more carbons, 1, 2. 6 carbons total. We start out with 4 plus 2 carbons, end up with 6. And then for mass balance, we have lithium bromide. I know I haven't been putting too much emphasis on mass balance, all semester long, but because we're doing harder, like carbon extension problems, you need to make sure you at least account for your carbons. So you have the correct number of carbons that you started with, you end up with. Conservation of mass, right? All right, so if we were to run this reaction with, so typically what you do with this reaction, after you think it's done, you add water to it, and this is referred to as a quench step. So if this has water around, this is a quench. Recall from lab, a quench step is basically what you do to make all the reagents unreactive. So you can go to your workup step, which is purification, basically. All right, so your standard acid base, so the same kind of arrow push. So this goes like that, that. And what carbon product do I have here? Yeah, butane. So it basically got its bond back to H. It's now just butane. And then I wouldn't worry about mass balance here. What else do I have? Lithium hydroxide. Yep, so lithium is our ion from here. And then OH was generated, so lithium hydroxide. Okay, just to recall from here, so I want to use a pKa discussion here. The pKa of water is about 15.7. The pKa of alkanes is about 50. Remember, equilibrium is going to favor the side that has the weaker base. It for sure favors the product side here. It does not want to be like this. It's super reactive. It would prefer to be like this. All right. The other reaction we could do here is, so we have our standard SN2s. This is a great way to extend carbon chains. We could also do reactions with what we saw with the epoxides earlier. So if I have this particular alkyl lithium compound, and let's suppose we have this here. I do want to mention here that it's kind of implied you're going to have a quench step. So sometimes people will drop off the quench step. But I want to go ahead and do the mechanism here. So here, why did I have it go to the left carbon rather than the right one? Less steric hindrance. This is SN2 route. So we're doing a base catalyzed ring opening, SN2 route. So SN2. So this group's going to go to the less substituted position. So we have our benzene ring. And then step 2 will be water. And then counter carbons here. Our new bond is going to be directly to the ring, like that. And then we have 1, 2, 3, 4, 5. And the OH goes here, like that. It's like a doggy. Never mind. Now you won't unsee it. Are there any questions so far about what's happening here? Okay. The other reagents that you need to be aware of are the organomagnesium bromide ones, commonly referred to as a Grignard reagent. The way we use these in lab, at least for this class, just go ahead and treat them as interchangeable with alkyl lithium. So you can use the Grignards or the lithium ones. Grignards are more common, though, in the real world. So Grignard reagents. All right, the way you make these is just like before, you take the corresponding alkyl halide, wherever you want the carb anion to be, that's where your bromine or your halogen should be. It's commonly done with bromides. And then what we need here is magnesium metal and ET2O. And basically what it's going to do, it's going to plug in magnesium right between the carbon-bromine bond. So Mg is now attached there. The way you want to think about this is basically a carb anion, the way it reacts. And I'm putting it in quotes because it's technically not correct. So MgBr plus. The reason why I'm putting a plus here is because magnesium ions are typically a 2 plus, bromides are 1 minus, so an Mg and a Br is a plus 1. And that is your counter ion for this, if it were ionic. The way you want to draw the reaction is exactly the same as we did with the alkyl lithium. So let's go ahead and take a look at a reaction. Let's try this. Let's try a couple different reagents, see what you guys think. So what if I use bromobenzene? What do you guys think? Would that react? So first things first, what mechanism was it? It's SN2. Can you do an SN2 with a benzene ring? You can't. No reaction. If you had water in there, that would be a quench step here. What if we used ethanol, trying to extend that chain? Would those react? Would you get a substitution? Nope, it would be an acid-base. So you get acid-base reaction happening here. So there is the protonated butane, the anion that forms, and then MgBr would be the counter ion for the alkoxide now. So what we can use this for is your standard SN2s. So I want to go ahead and do an SN2 substrate here. Let's say best with the primary ones. Let's use the same example from earlier. That would work. 1, 2, 3, 4. Original 4 plus 2 more. 1, 2. And then worrying about mass balance here, what do we have as our side products? Yep, magnesium bromide, MgBr2. The second bromine came from the leaving group of this one right here. Okay. Questions so far? All right, so the reason why this stuff is even in this chapter, we're actually still technically in alcohols. We haven't moved on yet. Is because this is actually a great way to make alcohols from carbonyl compounds. So far what I showed you guys was that we can do reductions on them to get primary, secondary alcohols. This is a way to get alcohols while simultaneously extending the carbon chain. So you're going to have to definitely count your carbons during this stuff when doing your homework. So here we had methyl magnesium bromide. So CH3, MgBr. And then the reaction I have here for an example, let's just change it up just a little bit from the notes. So you have butanal, aldehyde. I did mention to you guys back when we went over the hydride reaction that you can get nucleophilic attacks on carbonyl carbons, and that happens here. So the reason why this happens this way is because remember that this carbon is delta plus, this is delta minus. So that makes that carbon electrophilic. So we can do a nucleophilic attack like that. It looks like an SN2, doesn't it? The arrow push looks just like an SN2. The difference here is the leaving group does not actually leave. The leaving group is still attached. So keeping track of my carbons here, I extended my carbon chain by 1. And I'm going to draw this funny just to make sure that we're clear about what's happening here. So we have new bond, O minus, H is still attached, then the rest of the chain. So 1, 2, 3, 4. Okay, and then the last part here is just treat it with water. The water step will serve two purposes. One, it'll protonate the O minus. Secondly, if there's any left over Grignard, it'll quench it. So it'll go from your alkoxide to your alcohol and quench any leftover magnesium bromide compound. So final product here, 1, 2, 3, 4, 5. At carbon number 2, we have an OH. And then if we're worrying about mass balance here, it's MgBrOH.
What is exactly attacking the carbonyl carbon?
It's the bond between the carbon and magnesium. It's the bond. But in your head, you want to think about it basically, it's acting like a carbanion would. But carbanions don't really exist. We have them indirect ways this way. The water's bad, right? So I got another funny story for you guys. So typically if you take a majors lab for organic chemistry, they'll have the Grignard reaction in there somewhere because the Grignard reaction is super classic. And we only typically do it in majors lab because of how long the experiment is. Had this lab where we had to, it was at the end of one lab meeting, we had to clean our glassware and then wrap it in aluminum foil to put it in the oven until the next week. And I come in the next day, we had a step, we're doing a distillation with it, had the Grignard in there, and then I turn the water on. I turn the water on too high, the hoses pop, sprays water all over my glassware. So my teacher sent us home and gave zeros for that day. So I have gotten a 0 on an organic chemistry lab before. And it's because I botched the experiment. She was really upset with me. I told you to turn the water on slowly. But yeah. But my friend, who was my lab partner, whenever I do something screwed up, she goes, "Remember the Grignard." Like, I don't believe you. Remember the Grignard. It's like, whatever. All right. So if you run this reaction here, you get a secondary alcohol. We can run this reaction with ketones to get tertiary alcohols. So I have an example of that here. So point out here, this is a secondary alcohol. And we started with an aldehyde. So use that to help with studying. Same thing again, methyl magnesium bromide. And I want to react this with a ketone. Let's go ahead and use acetophenone for our example. Okay. And the second step would be water. And I want to go ahead and predict the product here. It's going to be similar. But notice now that we have a ketone rather than an aldehyde, we already have 2 carbons attached, right? So what's going to happen is you're going to get a third carbon on there. It's going to give you guys a tertiary alcohol now. So new methyl group. So let's go ahead and highlight the new methyl group. So I'm just being clear about what's happening here. So that's our new methyl group attached. We have the one that was already on there. We now have an OH and then our benzene ring, pH, like so. Okay. Actually, let me change this compound just a little bit and I have another question for you guys. So I'm going to add this 1 carbon there just to change it just a little bit. And the biggest thing I did here was I made a chiral center. This is now a chiral center. So the question I have for you guys, would you expect there to be 1 enantiomer or would it be racemic? Heard someone say racemic?
What?
So what is the hybridization on this carbonyl carbon? So what happened before we had that carbocation during SN1, right? Where we have a flat molecule that the nucleophile can attack either face. The exact same thing is happening here. This molecule, that carbon is trigonal planar, sp2. So trigonal planar. And if you have that kind of situation, your nucleophile could attack either face of that molecule, giving you both enantiomers here. So this is racemic. So if you're being asked to specifically show stereochemistry here, these are racemic. All right, I think I want to show you guys one more reaction for the day, and I think we'll call it good. I did have some synthesis here, but I don't think we really have time for it. All right, so another reaction we could do here is if this reaction is done with esters, that is another way to get a tertiary alcohol. So it's the same methyl magnesium bromide, and I think the ester I want to use today, let's go ahead and use nail polish remover, ethyl acetate. Oops, I want to make my carbon a little bit longer. All right, there you go, ethyl acetate. Commonly called nail polish remover. All right, I did want to go ahead and work out this mechanism. So the first thing that's going to happen is you're going to get a nucleophilic attack on the carbonyl, just like before. So boom, like that. We have a methyl group attached now. We had the one that was already on there. We have an O-, that's this oxygen here. We have this happening. Okay. So we're going to go over this a lot more detail during the carbonyl section, but I do want to mention that at this point, what can possibly happen is if the carbonyl is going to want to try to reform, which is pretty normal. So if the carbonyl reforms, in order for that to happen, something has to leave. So if there's a good leaving group, something may leave. And it works out in this case where this works as a leaving group. It's not the best leaving group, but if you think about it, this is a much weaker base than the base that came in. The base that came in was super strong. This one's just kind of strong. So this will actually leave. This type of step is called an acyl substitution. So I want to make a note of that here. This is an acyl substitution. We're going to have a whole chapter for that type of substitution. So don't worry about it too much now. I just wanted to basically point out If you're replacing a group on a carbonyl, we call it an acyl substitution. So no longer SN1, SN2. All right, results is we now have acetone. So I want to say minus OET negative here. That was our leaving group. So what can happen now is we now have a ketone, which earlier I showed you guys that these can react with Grignards. So if there's any more Grignard around, this will react as well. So this attacks the carbonyl, pops that open. We now have almost a tertiary alcohol, O minus. And then the quench step would then happen, second step water. We now get a tertiary alcohol. Oop, should be OH. What's that? Yeah, so if you, that would also quench the ethanol. It would make it just ETOH instead. But I'm just worrying now about the fate of the main carbon substrate. All right. Questions, comments, concerns? All right, I'm going to go ahead and leave you guys with the practice problem I recommend. Well, I wanted to work it out today. We'll just do it next time, but I'll give it to you here. So starting with these two compounds. So we have isopropyl alcohol, bromobenzene. We're going to put them together. And make that. So question, what reagents do that? So when you're connecting two molecules like that, the first thing you want to do is recognize which half came from what molecule, and then try to identify how it can get a nucleophile electrophile thing happening here. That's how they're always going to connect. They're going to have one of the nucleophile, the other one of the electrophile. How do they come together? And that's what you got to figure out. Probably the Grignard. All right, so let's go ahead and stop here for the day. You guys had enough OChem for the day, I think, probably. All right.